Hey guys, welcome back. Today we're going to discuss, again from Unit 1.2, Chemistry and Living Systems, but we're just going to have a very brief conversation on chemical reactions. That's our Part 4 notes. We're not going to get into a whole lot of detail. Most of that would be more in a chemistry class, but we are going to discuss a little bit about it, just so you have some kind of foundational knowledge that'll help you understand how the reactions in your body occur and things like that. So again, it should be super quick, not very long section at all. All right, so you guys ready? Shall we shall. Let's go. So let's start off by simply discussing what is a chemical reaction. So a chemical reaction is a process to change substances into different substances by breaking chemical bonds and forming new chemical bonds. So in other words, all we're doing is rearranging the atoms. We're not adding anything new to it. We're not taking away anything from it. We're simply breaking existing bonds between the molecules, rearranging the atoms, and forming new bonds. You kind of tell in this picture, we have two red circles that are on their own, and we have two blue circles that are bonded together. So what's going to happen is we're going to separate these two blue circles, and then each one is going to bond with a red circle. Now notice we start with two blue and two red, and what do we end up with? Two blue and two red, but they're in a different combination, and that's all a chemical reaction is. So how do we write chemical reactions? Well, it's kind of written like a math problem almost. And what I mean by that is you begin with one side. So what are you starting with? We call these the reactants. So it's in terms of the math equation analogy, what numbers do you start with? And then we have an arrow that's kind of like the equal sign in the math equation analogy. And what we end with, your answer in a math problem, we call that the products. So as we see here, you can do it in terms of the picture, but normally it's easier just to write it out using chemical formulas. So we have one black circle, that's carbon, 1, 2, 3, 4 white circles, that's hydrogen. So we have one C, 4 H's, CH4. And then we have two red atoms bonded together and another two red molecules bonded together. Now, these are O2, so it's two oxygen bonded together, and we got two of them. That's why we see this big 2 in front. So O2 with the little 2 refers to one of these, but we have two of them, and that's with the big one. So what we're saying is we are beginning, our reactants are 1 CH4 plus 2 O2 molecules. You don't have to put a 1 in front of the CH4 because it's implied, just like in math with variables like x. You don't have to put a 1 if you only have one x, because the fact that you wrote x means that there's at least one. Same here. The fact that we wrote CH4 means we have one CH4. If we had more than one, then we would put a big number in front of it, like we did here. So we have one carbon with 4 hydrogen, so that's 1 CH4. We have oxygen bonded to oxygen, that's O2, but we have two of them, so 2 O2. And when we break the bonds and rearrange them, we end up with our products. So these were our reactants, and these are our products. So remember, we had one black circle, which was carbon. Here's our one black circle, which is carbon. We had 4 white hydrogen, 1, 2, 3, 4. 4 white hydrogen. 1, 2, 3, 4 oxygen. 1, 2, 3, 4 oxygen. Notice we didn't add anything else. There are no new atoms included. And we're not missing any atoms. Everything is accounted for. But we made new substances out of it. So carbon and 2 oxygens is CO2, carbon dioxide. And oxygen with 2 hydrogens, that's water. We made one molecule of water and another water molecule of water. So we have two water molecules, two H2O. So from CH4 plus 2O2, we can get CO2 plus 2H2O. Everything in terms of the atoms are the same, but we broke the bonds, we rearranged the atoms and formed new bonds. All we did was make a new combination of molecules from what we had. Kind of like if you have Legos and you build a house and then you think, I want to make something new. So you tear apart your house and you use the exact same Legos to make a spaceship. You have all the same stuff, but you rearrange them to make something new. That's all a chemical reaction is. All right, so how do they occur? Well, all reactions need energy. They need energy. And that's the reason why they can occur, is because energy is present. Kind of like us. If we have no energy, we just kind of like lay around and be like, But once we get energy, we can get up, we can do things. And what we call this is activation energy. So what happens is energy is actually present in two ways. Energy is absorbed into the reaction in order to break the bonds. And then when the bonds are broken, they can release additional energy that was stored within them. Now, the energy that it takes to break the bonds, we call this the activation energy. So that's the energy needed to start or to activate the reaction. Now, a lot of times this can be done using heat as your energy source or light as the energy source, but some kind of energy needs to be added into the system in order to begin the reaction. So energy is added to the system, which allows the bonds to break. When the bonds break, they release stored energy, energy that was stored when the bonds were first formed. All right, let's see. So total energy. Now, depending on the amount of energy that is absorbed in order to allow the energy to occur, so activation energy versus the energy that's released, we can classify reactions as exothermic or endothermic. So in an exothermic reaction, you actually release more energy than is absorbed. So some energy is absorbed to break the bonds, but once the bonds are broken, they release their stored energy. There was more energy stored in the bonds than is needed to break them. So what happens is energy goes in, more energy comes out. So once you break those bonds, it releases this plethora of energy. Typically, this excess energy can be lost as heat or light. So some examples of this would be, if you've ever used those like little hand warmers, you have to crack them in order to allow the different chemicals to mix. And once they do, it gives off heat and it keeps your hands warm. So that's just a chemical reaction. What's going on is once you break the barrier that separates the two chemicals, they mix, they react together. So a little bit of energy goes into it to break the bonds, but a lot of energy comes out when the bonds are broken. So the stored energy that is released in the form of heat. And that's why a little packet will keep your hands warm in winter. Same with glow sticks. You have a glow stick, you snap it in a few places, and it breaks those internal barriers, once again, allowing the chemicals to mix. Once they mix, it allows for a chemical reaction to occur, and they start to glow. That's the excess energy being given off. So a little bit of energy went in to break the bonds, and then the energy that was stored in the bonds was a lot more than it took to break them. So the extra energy is given off as light. Endothermic reaction is the opposite of that. It takes more energy to break the bonds than the bonds had stored within them. So that means that not as much is released, more was dragged in. So what happens as a result is, because you need more energy to break the bonds, is going to absorb energy from the surrounding area or the surrounding environment. If you've ever mixed baking soda and vinegar, it's a really common reaction, one that most kids can even do at home. It causes, the bubbling, the fizzing, and it does release carbon dioxide gas. It is a chemical reaction. But if you've ever touched the container that it's going on and that the reaction is occurring in, it feels cold. And the reason why it feels cold is because the reaction is actually sucking the warmth out of the surrounding area. So it's not that it's giving off coldness, it's absorbing the heat energy from everything around it. So it absorbs the heat from the cup or the container or the beaker, leaving that object feeling cold, because the energy that was allowing that object to feel warmer or, room temp has been sucked into the reaction in order to break the bonds. So this is just kind of what we were talking about. Pretty much we're just looking at which side is bigger. Here in endothermic reaction, we have bigger energy, more energy going into it, and a little bit coming out. As opposed to here, we have a little bit of energy going in and more energy coming out. So exothermic. It's the size of each side is pretty much a reflection of how much energy goes in. A lot goes in. Notice how this side is longer than this one. So more energy goes in, not as much is given out. So more energy goes in than was released. Exothermic is the opposite. Not much goes in, but a lot comes out. So more energy is released than was given up or than was required. All right, so let's talk about living systems specifically. We have these things called catalysts. And what they are, they're actually substances that can increase the rate of reaction. The nice thing about these is they are reusable. So what specifically occurs is you have something that you can add to a reaction to make the reaction go faster. And as you can see in this picture, this right here is our catalyst. It provides a location where it can actually pick up particular molecules or atoms, bring them close enough that they can react, and then once they bond together, it releases them. So it allows a common area. It's kind of like, I'm going to grab this atom and this atom. They're now close enough they can react, let them bond and go on their way. And then grab another and another, allow them to react, go on their way. Grab another and another, allow them to react, go on their way. Now, in living systems, we have particular catalysts called enzymes. These are a type of protein that do the job of a catalyst in living systems. So we have enzymes in our cells, and they help us do a whole bunch of different functions. Now, I talk about different functions. I'm not talking about necessarily as broad as heartbeat or things like that. I'm talking about even on a cellular level. Yes, on a systems level, we have enzymes in our saliva that start the digestion process. We have enzymes in our stomach that continue the digestion process. But what I'm also talking about is within each individual cell, there's a whole bunch of enzymes that do different jobs. Some enzymes will break apart and recycle materials. Some enzymes will help build new organelles or will help to build new DNA. But they do these essential functions because honestly, without them working, a lot of these functions would take too long. The cell would die in the meantime. And if the cell dies, you die. And we don't want that. So the nice thing about enzymes is, like we were saying with this picture, they provide a space for the reactants to actually get close enough that they can interact and go through a reaction in order to form the product. All right. So additional resources, we have Science in Pajamas. It's the chemical and physical changes one. You might have seen this one linked in the part 1 notes. Since we're not going into a whole lot of detail on different reactions, I just thought this would be a good kind of reminder of what chemical reactions are. If you've already watched it, great. If you haven't, maybe check it out. Some other videos that go into a little more detail, we have Atomic School, which does an introduction to chemical reactions. Just like we said, kind of explaining some of the stuff we've talked about in the notes. TED Ed, so that's educational TED Talk, what triggers a chemical reaction. Fuse School, what are endothermic and exothermic reactions? Yep. And then Don't Memorize, which is an introduction to chemical reactions and equations. So a lot of these videos are going to have probably way more information than what we've discussed in our notes, and that's fine. Nothing bad with getting a little extra information. But I just wanted to introduce the idea of chemical reactions to you and start letting you know how they affect our cells. The link for this presentation will be in the description. If you have any questions, let me know in class via email or through our Google Classroom. But in the meantime, you guys, stay awesome, stay curious, and most importantly, stay safe and healthy. All right, you guys, take care of yourselves.